All right, so here we're going to continue the review here. Here's section 3.3. In 3.3, we're talking about solids, liquids, and gases and being able to distinguish them from one another. Remember here, I'm not going to try to write too much on the screen, but remember the arrangement of the atomic structure of the solids is that the atoms are very close to one another. So this is going to give you a structure in which the solid phase is going to be identified by a very rigid pattern. And the way I've represented them here essentially is just an alternating, just fitting into the various gaps. But in two-dimensional space, but if you do this in three-dimensional space, you can see that you're going to wind up getting a crystalline or a amorphous type of structure. In terms of the crystalline, remember that means that there is a repeating pattern in the cell, a basic unit configuration, and that's what is being repeated over and over again in terms of the units. With regards to the liquids are very similar to the solids in the sense that the atoms are close to one another, but the main difference between the two is that the atoms of a liquid here, these are able to slide past one another. They're able to slide or move. And that's a very important thing because the solids are actually very rigid. They're not going to move, so they're fixed in position. And so that largely influences the structure that they're going to have. Solids typically will not take the form of the containers they are placed in. They retain their shape. They have very distinct shapes. Liquids, that because of the moving and sliding of the atoms, they're able to take the shape of the container that you place them in. And so that's important there because that particular structure is going to be very fluid in a sense because it can actually change. Not because there's a lot of space between the atoms, but rather because they're able to slide past one another. Now, the atoms of gases are different. Here, I've kind of drawn just 3 atoms of a gas, and notice the difference here is that there's a tremendous amount of space between the atoms here. And so that leads to another property that's observed in the phases that matter, is that is the compressibility factor. Both solids and liquids cannot be compressed, whereas the liquids here, the liquids actually can be, they're highly compressible. And so that's going to be very important for us to consider. Now, with respect to intermolecular forces, because all this time between units 3.1, 3.2, and even in unit 2, what we've been able to do is that we've been able to look at the intermolecular forces. And so with solids and liquids, what we see here is that there is a difference in the intermolecular forces with regards to them. And so that means here with the solids, they're going to have high IMFs occurring here with the solids. With regards to the liquids, in comparison to a solid, they're going to have lower values of intermolecular forces. So those forces are a little bit lower. So we're just going to identify that as weaker IMFs. But when you compare the liquid to a gas, clearly the liquid is going to have a stronger intermolecular force than a gas. And so that's one of the differences or one of the things that we see here with regards to whether it's able to enter the gas phase or not. Typically when we compare two compounds that might be in liquid phase, which one is more likely to enter the gas phase compared to the other. And so just to finish off the thought here, for the gases here, they have a very low intermolecular forces of attraction, especially when we start to consider the difference between a real and an ideal gas, which we will talk about here shortly in the next couple of sections in 3.5. So those are the main things that we identify here with both of these. However, solids and liquids, they have one important characteristic, and that is that they actually have similar molar volumes. And so this is important only because when we talk about the amount of matter that is present, both solids and liquids are going to have very much the same amount of matter occupying a very similar amount of space. And so that's important for us to keep in mind there with regards to that. Gases, on the other hand, are going to occupy a tremendously more amount of space, and that's largely because gases are able to spread themselves out over any given area or volume of space. So that's more tied to the issue of diffusion, effusion, but they do occupy more space. Now, when we consider things like standard pressure, temperature, then we need to consider the volume there. Gases occupy a volume of about 22.4 liters, but that's more of a topic that we'll discuss a little bit more here in section 3.4. But that's actually the things that kind of distinguish the three. Now, the other item that we need to talk about here is how does one go from one phase to the other? And so that's something that you should be aware of here. Because when you move from one phase to another, that's actually a function of the kinetic energy. So on this level, kinetic energy actually does differ between the three phases. And so if we look at solids in particular, and so let's kind of do it this way here for solids. Solids actually are going to have the lowest kinetic energy. The ones with the highest kinetic energy are going to be the gases. And so I'll put that over here in purple. So this is going to be the highest kinetic energy of the three. And in the middle, you're going to have liquids. So we're just going to say middle kinetic energy for the liquids. Now, obviously, the kinetic energy is actually a lot closer to a solid than it is to a gas. But if you need to rank them, the liquids have the middle ground in terms of kinetic energy. Now, that actually is going to be very important as we start to talk about the phase changes, which is another section that we talked about here. Now, you don't need to memorize all of the different phase changes that were there. Just be familiar with what they are. And so let me kind of get another slide here or move some of this stuff over to the right, and I'll show you some of that information. And so let's see here. We just go ahead and do this. Let's kind of put everything over here on the side, minimize it like that. And let's put some of this information over here. And put these over here as well. All right, so now that we've got that there, let's talk about the phase changes. Now, the one thing that you should be familiar with is going to be the phase diagram. So remember, the phase diagram looks something like this. I know it's not going to be drawn to scale, so please don't hold me to it, but essentially you have something like this, and then it'll go up a little bit like this and something like that. And temperature here, we're going to put some variables here. Temperature is going to increase that way from left to right on the x-axis, and on the y-axis, pressure increases as you go up. So the main thing for you to remember is where the phases are. So solids are over here on the left-hand side. So low temperatures to low pressures all the way. You can have very high pressure or very low pressure, but at low temperatures, we're going to have solids largely because the kinetic energy is very low. So remember, the kinetic energy is going to be directly proportional to temperature at the absolute level, in terms of, in other words, at Kelvin temperature. So that's why we get solids at very low temps. And so the next item here is going to be where we find the liquids. So liquids are identified here. And let's just put gases for now. And so you should be aware of that. So essentially here, when we look at the solids, the liquids, and the gases. Gases can exist also at low pressure, but notice here they can also exist at low temperature all the way through as well, but largely when we have low pressure. And so that would be one of the conditions for ideal gases. Gases prefer high temperatures and low pressure, and so that's kind of what we see here for the gases. Liquids tend to occur when you have moderate levels of temperature and moderate to high levels of pressure. And so here we see the liquids right here in the center. So it's not important to remember all of this, but remember, just know where they're at and be able to identify if you're given conditions. For example, what if you have conditions of low temperature, high pressure? So if I were kind of doing this, I would say, okay, well, then that would say that we have low temperature, high pressure, and then all you need to do is kind of identify where these two conditions intersect. And so what I'm doing here is just a drawing here, and notice that they're going to intersect in this region right here, which essentially is tied to a solid. And so that's the main thing to know there. Okay. Do keep in mind the other principle, or the other main idea in this section, is going to be here that as the temperature increases, this is going to be directly proportional to the kinetic energy of that substance, whether it be a solid, liquid, or gas. So when the binding energy, when that lattice energy of a solid is overcome by the kinetic energy, then the solid then will transition over to a liquid. And when the intermolecular forces of attraction that are essentially greater than the attraction forces of, say, cohesion, then what you're going to see there is that you're going to see the liquid then advance over to the gas. Now, movement from one phase to another is not linear. You can go in the backwards direction as well. So I'll put a double-headed arrow on all of these because you can easily go forward just as much as you can go backwards. Okay, and so that's the main thing here in this section when we talk about the various gas phases. Okay, and so remember all of that. Oh, and one thing I'll make sure I say now because I might forget. I almost did. And so here's the other big thing here, and I'll put this as an exclamation part down here at the bottom. So just remember that phase changes here do not affect intramolecular forces. They will, however, affect intermolecular forces. So whenever you go from one phase to another, that's why one of the reasons why those molecules are able to go from one phase to another. And that's largely because those intermolecular forces, those hydrogen bondings, dipole-dipole interactions, or the London dispersion forces, those interactions, those three, and perhaps even the ion-dipole interactions, should they exist, all of those are the ones that are going to be affected by changes in temperature. They're the ones that are occurring between atoms within a single molecule. Those are not interacted or affected at all. So it's important that you distinguish that as well. So that's pretty much it for section 3.3. It's mostly about the intermolecular forces, phase changes, and just being able to identify how intermolecular forces or changes in those forces are going to lead to the phase that the sample is at, either whether it be a solid, a liquid, or a gas. So we'll continue here with 3.4 in the next video.